All right. Welcome back to the weekly Open Studio design session. Last time we got started on a new project. We finished off the X47 as well as the Rapid Prototype 004. So those two projects are still in the queue for video. So I'm going to work on that. Just need to wait until I get my new SD card that I ordered. It's 1 terabyte, which is a lot, but hopefully then I can use my full frame and get some better quality video to work with. But yeah, those two projects are, sitting by the side, and last week we got started on a new project, which is the F16, which is a real-life design. It's a little bit different because it's been a while since I've actually done a design based off of real life. Last time we worked on the fuselage and got that down. So that's right here. We'll just move some of this stuff out of the way. We also got a wing template right here. It's kind of hard to orient which way is the correct way. I think it's this way. It's a little bit, the tip here has to be pretty thin. So, yeah, but we'll figure that out as we go. It's an interesting project because I haven't actually made an F16 before on this channel, and so now with these new techniques and whatnot, revisiting real life designs, it's gonna be interesting. So this is really supposed to be a simple build. It's just a basic wing and then elevator, right, and then just one tail. So it's a pretty simple build, but I actually want to be able to incorporate some new things into the design here. So I will be incorporating a mechanism for the slats and horizontal stabilizers, which are linked together. So that way, when you pitch up, your elevators kind of tilt in like that, pitch, they turn up, and then your leading edge slats, they're oriented the same way, so it's easy to align those two control surfaces together. And this is like a benefit of kind of like the traditional wing tail design, is that you can synchronize the flaps or the leading edge slats with the elevator surface. You can synchronize both of those together. This is a little bit different from like a canard configuration, which, let me just grab an example real quick. Alright, so as you can see in this example, this is the YX10 Astra. As you can see, I've worked a little bit on this. Just covered the bottom part here, but this is still very much a work in progress. I don't plan on doing like a live stream while working on this, because this is like a project that means a little bit more to me, so I need some time to like think to myself and really work on this, not on a live stream. But anyways, I was getting at this point, which is that, you have your leading edge slats, right? And you have your canards. So if they were linked by one mechanism, they would have to go in the same direction, unless you do some mechanical wizardry. But I'm not exactly a wizard. So this is interesting. When you have this surface in the back, right, when you don't have a canard surface, when you have like a traditional tail surface, when you synchronize the movements, it actually works together because your plane is pitching up and your slats are down, which helps guide the air over the wings, right? But, in a canard configuration, it doesn't really do that, at least not for this design, because this is a lifting canard design, which is slightly different from, like say a Sukhoi Su-30, right? Because in that plane, the CG is actually a little bit behind the center of lift, and so that results in a pitch unstable configuration. So whenever you see it pitch up, the Su-30 actually points its canards downwards, which is very interesting. It's not a lifting canard surface, it's more like it's like a slat in itself, right? So, but anyways, that's not really the point here. The point is, for this design, for the F-16, we're able to synchronize the direction of the movement of the control surfaces. So instead of canard, we have a regular tail, and we have regular wing slats, right? And we're able to synchronize them going into the same direction. So I kind of want to be able to incorporate that into this design. So that might make the build a little bit more complicated, but otherwise it's a relatively simple build, right? You have a triangular wing, cropped, right? Cropped wingtip, right? Because it's not a sharp triangle. And you have a regular tail, as well as a single vertical stabilizer. So it's a very straightforward design. Hopefully it shouldn't take too long, but I feel like what would take a very long time is the actual mechanism itself, because you have to align it properly in the right location. It all has to be integrated properly. So that's the only thing that might make this build a little bit long. But I'd rather make a great plane in multiple sessions than make one and not learn anything, and then you don't really improve on your next one. So I want to push the limits of what I can do right now. I'm going to incorporate the latest mechanisms into the new design here, the F-16, and we'll see how it goes. This is a little bit larger, actually, now that I'm looking at it, compared to what I usually do, because my old method for creating these planes was to use a regular paper airplane and then build off of that. And usually that base regular dart paper airplane is a lot shorter than what we have here. It probably ends about here, so that would scale down the wing area by quite a bit. So this is actually a little bit larger than I normally do for a design, but we'll see. We'll see how it goes. We're gonna use some new, I guess, strategies, configurations, right? We're gonna use wooden wing spars to get a very rigid design, really resilient design, instead of using a conventional straw, which actually makes the wing thickness really large. With a wooden configuration, you're actually able to get a much thinner wing, right? So if you look at this, let's see if it focuses, but you can see the wing is actually really thin here, compared to some of my other previous YX prototypes. So thinner wing, less drag, better performance, right? But the trade-off is you get worse stall performance, because the air, once it strikes a very sharp surface, it doesn't know what to do. It's like, and then it just stalls, The air separates, and then your wing stalls. So to counteract that, that's why the slats are so important in a very sharp wing, is to get some of that airflow to flow over smoothly. So yeah, we're gonna get started here. Right now we have the template for the wing, template for the fuselage. We have the actual fuselage core, the base design here, base planform. What I'm thinking is I'm gonna need the wings, because really at the core of this design is the actuation mechanism that links both the tail and the slats. So I'm gonna need the wings made with the slats cut out and ready to go before I can start working on the mechanism, right? Because that way we get a layout of what to do, and I think, you know, also just having the tail there, it helps you visualize kind of better, you know, what we're about to do. So I am going to start working on that. Again, this is an open studio design session, so please feel free to work on your own projects in the meantime. Don't feel like you have to just, you know, stick around and watch this. You put it on in the background, listen in like a podcast or something, and work on your own things too. So let's get started. I am going to grab my iPad real quick to get the shape of the vertical, or not vertical, the horizontal stabilizer, so I will be right back. Alright, so I have the Trace app open right now. Just grabbing a photo real quick. Okay. This is the same photo that we used last time. This is actually a diagram off of Wikipedia. Just make sure I don't have anything running in the background. Alright, we should be good. To get the same scale that we had before, I'm going to align it. That's pretty close. I think the way I aligned it was the tail is right at the edge and the nose is right there at the front. So this is pretty close to what I have. Yeah. Just looking at this a little bit more closely. This doesn't. Just matching this up. Alright, so it's a pretty close match. Doesn't have to be exact, right? Not making a scale model, making something that actually flies. So the requirement is not as stringent as, you know, those professional plastic modelers. Alright, so I'm gonna copy that shape. Do just that. I'm gonna line it right up to the edge. That way I don't have to draw many points. This saves on time. Again, you don't need an iPad for this. It's just convenient to have an iPad with an app that does this, but you can use any large format monitor, really. As long as you don't, you know, draw too hard and damage it. Right. So this point and this point, that's really all you need. You just glean some information off like that, and you should be all set. Alright, so I'm gonna take a sip quick. Gotta stay caffeinated for these sessions. Anyway, I'll put this to the side real quick for a second. We're gonna grab a ruler. Fixing my chair real quick. Alright, come a little bit lower here. Alright, so move a little bit closer so I don't have to reach too far. Alright, so you just use the information that you gleaned off of that drawing. This is the nice part about doing a real life design, is that you don't really have to think too hard about the design because it's already there, it's already determined. The only thing you have to do is try and match the design as closely as you can, and know where to make sacrifices for, you know, making it look real versus making it functional at your scale, right? Because in the end, this is just, you know, a glider. It's not a RC plane or anything, but there are certain features that you want to be aware of, and you want to try and make it work, you know, convert it, so to speak, to your format, to your scale. I don't know if that makes any sense, but I think I saw a comment earlier. Interested in how you model the intake. Also, how will you tackle the bubble canopy? That's very interesting. Those two things are like kind of the defining characteristics of the forward fuselage portion of the F-16. I have some ideas right now for the intake. It's gonna be a little tricky because it has that diverter plate, right? So essentially you have, you know, I'm just gonna sketch real quick to convey the concept here, but you have your plane, right? And you have your, you know, bubble canopy, whatnot. And then you have your tail here in the back. And then, you know, your stabilizer there, your main wing here, right? On the F-16, the intake, you know, it's very interesting. It's like this gap that's right there. Right, and then you have your, you know, bubble canopy or whatnot, and then tail and whatever. But down here near the intake, it's there's a gap here with this cross section. If you look from the top, is like this. It's like an airfoil shape, except it's symmetric, right? And then this is like a plate. It's hard to describe exactly what it is. It's well, this isn't a plate, but the intake itself is like lowered from the aircraft itself, right? So this is not to scale. This looks completely wrong. It doesn't look like the F-16 actually, but right, the intake is lowered from the fuselage, and the reason for that I explained in a previous video. Is you know, you have your surface with air flowing over it, right? But okay, so let's look at this, right? So imagine like you have your wing right here, or any surface really. The way they draw it in class actually is more like this, right? You have a sharp leading edge. Yeah, it doesn't matter the bottom, so that's why it's slanted down like that. But when you have air coming here, it strikes this location at the tip, right? If you look at the velocity going away from the surface, it's uniform, right? Pretty uniform. But then as you start going back at time, let's say 1 second, 2 seconds, 3 seconds, but it doesn't have to be any actual time, you start to have, you know, these profiles, right? So here, out here, it's still pretty fast, but because of friction, you're slowing down the air close to your skin, right? And so you have this velocity profile. And then so it gets worse, right, over time. So really this should be like, be more out like that. And then this is like a little bit worse. And then this is like really bad, right? Because it's really slow down here. So essentially what you're doing with the splitter is, you know, with that gap, is you're slicing it off, right, at a certain location. So on the bottom here of this F-16 intake, you're really seeing a distribution something like this sticking to the fuselage because, you know, your nose hits the air first, and then so your air really close to the skin is really slow. And so right before the intake, the velocity profile is going to look something like this, right? And so what you want to do is drop your intake and then cut it off, cut the air off at a location where it's relatively uniform, right? This is uniform air. And then this goes into your engine, which then can run properly because the intake is not receiving dirty air, so to speak. And so that's kind of the theory behind this design. On the F-35, they don't have that. F-22 does have that little gap, if you notice, between the intake and the fuselage. But the F-35 uses new DSI technology, which is diverterless supersonic inlet. It's essentially a bump. Like imagine like instead of this configuration for the structure, it's more like you have a skin panel and like a portion of it that's like contoured out, and like you have a bump and then the intake comes down like that. This takes a lot more computation, which is why it took a lot longer to incorporate this, right? Because you have to get the flow field around this bump to be uniform going into the intake. So anyway, that's kind of the theory behind all of that. But how am I going to model the intake? That's going to be interesting. I feel like, for a design like this, maybe like a structure, minor structure with tabs, right, to attach the inlet to, right? So you have like a tube, but then you also have this structure, right? And then you have tabs coming off of that structure. Or something like that, and then you can have tabs on the other side to connect to the fuselage or whatever, but we'll figure that out as we go. Right now we just want to get the core of the design well done, which is the control surfaces linked together through a mechanism. But it should be an interesting project. See how well I can pay attention and model a real-life aircraft. So that's my plan for modeling the intake. Just kind of winging it, no pun intended. Just kind of see how it goes once we get there. But that is a defining feature for this plane, so I will try and get that correct. As for the bubble canopy, I was experimenting. Well, I guess not really experimenting. So I live in an apartment right now, and so I don't have like access to like bottles of water, right? Because usually I get bottles of water because it's a little bit cleaner than apartment tap water. So since I ran out and I don't want to go out and in these times to get new water, I have been boiling water at home and then pouring it into plastic water bottles that are left over that I have, and then putting them in the freezer, right, to cool it down so that I'm able to drink it at room temperature or even chilled water. So what I was getting at there was that when I actually poured the boiled hot water into the plastic bottle, I noticed that the plastic itself actually started to deform a little bit, and I was wondering if I could use that to my advantage in modeling the bubble canopy here. The only tricky thing about that is you need a mold, like a predetermined structure to wrap that plastic around to get that shape. So I don't know how to make a mold for that, and so that's kind of why I haven't actually attempted to really do that yet. But I'm assuming like I could find some round shape to approximate it you know, maybe like a Sharpie marker or something, right? But, you know, the size has to be right, the general shape has to be right. So there's really a lot of things that don't work. So I am not sure yet about what exactly I'm gonna do there. So I think for the tail, it actually comes off the end a little bit. Let me just grab the iPad to take a look at the design. Alright, just lock this in place. Yeah, it goes a little bit beyond the tail there. So for my reference, I'm going to mark the location where it comes off. Alright, so this is kind of how it matches, right? And then the leading edge starts here, trailing edge of the wing starts here. The wing comes off here, but really it goes all the way. Well, I mean, I guess that is the wing where it ends. But I should draw perpendicular lines there to mark that, really to get it down. Alright, so I'm going to mark this. So yeah, sorry, kind of my mind is like all over the place, but that's kind of how I'm going to tackle the bubble canopy, is try and use a new material, which is plastic waste, right? That way you recycle, right? Make use out of the plastic, and you can also help the environment that way. Just measuring, just make sure 3.5, 1.5, a little over 1.5. A little over 1.5, yep, 3.5. Yep, pretty close. Looks good. This is where the wing comes out of. Shoot. I wanted to notice like how this works. I thought it would be a little bit forward to match where that curve ends. Just reference it real quick again. Yep. It doesn't end there. So if you notice, there is a little bit of a horizontal area right here. It's like very slight, and then it starts curving down. So we have the geometry right. So that's kind of what I wanted to check there. All right. So now that we have these templates, we need the actual parts for these surfaces, so we're able to get a better feel for what the mechanism is going to look like. We can get the tail surface relatively easy. Right, just try and carve the shape out of some scrap that we have from previous projects. Tracing this template onto cardstock. Right. mark that out. Try and maximize usage. So minimize the amount of cuts. Okay, we have those two parts marked. While I'm at it, I'm gonna get the wing marked out too before I start cutting all of the pieces. Earlier in my stream that I actually thought the size of this airplane was relatively large, but now looking at the wing, it's not all that large. It's well, maybe it's because I'm just looking at one wing, but you have to remember, right, part of the wing is cantilevered, so that means a part of it is actually inside the fuselage to get a better structural, performance. So it's actually even smaller than what, this is the actual wing itself. It's right. It's not that, get a better feel. But we're getting there. Just want to get the templates done, copied onto this actual part, and then instead of doing it like that, could try and minimize waste here. Figuring out a good way to do that. Alright, so this is going to be pretty close. Okay, so now I have the two wings done. So you might notice there's a tiny gap in between the two. Very hard to notice, but there's a slight gap, and that's done on purpose. If they were coincident, if the lines were coincident, any error that I make in the cut would result in both pieces being kind of off a little bit, So that's why I chose to separate it just a little bit, so that if I were to make a mistake, it doesn't ruin both pieces. For the actual cut, I feel like I should use a better tool than just my scissors. And since I already have this tool at the ready, I can just use it. Save some time. All right, all you gotta do is align it. Make sure you don't cut too much. About right there. That's a straight line. To simplify my build, I am going to make a cut across the entire sheet here. This will make it a little easier for me to cut. Right, because now you only have this material right here to deal with. Um, this is gonna be hard. It's a diagonal cut. It's not straight onto the edge. So it's gonna be kind of hard. All right, that's a pretty clean cut. All right. That's the thing, right? Most people, I don't want to stereotype, but there are those accounts on Instagram and whatnot that create wonderful renders. You know, they're great. They look great, but they're unrealistic sometimes, which, you know, kind of bothers me. But, you know, you have to be a little unrealistic at times to kind of push design forward, right? So I'm all for new ideas, but it has to be within reason. I'm just kind of ranting right now, so if you don't want to listen, you can mute me or something. But you really have to understand how manufacturing works in order to get a better appreciation of how things are, right? Okay, that's a pretty clean cut. Not too bad. You notice I took a little bit more time with that cut because it was a critical cut. You know, I didn't have to put it so close together, but in order to save material, always try to be efficient with the material that you have, right? Don't take it for granted. It takes a lot of energy to create these sheets, a lot of heavy machinery that you don't notice behind the scenes. So energy cost, material cost, it all adds up. And even though this is a hobby, you want to try and not create too much waste. It also is good financially not to waste any material. So if I could recycle my own paper, I definitely would. I just don't know how to recycle paper, or if it's even possible for a hobbyist to recycle their own paper, because the process is just, you know, at that point might not even be worth it, right? If you can recycle your own paper, then why would you, you know, go out and yeah, I'm just like ranting to myself. This doesn't make any sense, really. Just thinking to myself. I tend to do that a lot when I think deeply about things. Yeah, for these smaller cuts, it's perfectly fine to use a pair of scissors. It's when you like have to make more than one cut, it's easier to just use the straight edge cutter to get a very, very straight edge. There's a couple of YouTube videos out there. I don't know if you guys have seen them, but it's very interesting. It examines the definition of flatness and roundness and straightness, right? And how we got to this point, right? Because the very first tools were very crude, but over time, as technology advanced, you know, going through the Industrial Revolution, we're able to get better and better tools and machines, and now we can create like super fine, you know, I think it's like EDM, right? Electron deposition, machining. You essentially blast electricity to cut a metal block. It's insane. Like, the tolerances are amazing. So I don't know, it's just like a couple of YouTube videos that I watched. They're really good for learning, you know, the latest and greatest in manufacturing technology. It's really, you know, like, people want to say that the future of aerospace is, you know, all computational, which, you know, I agree with. A large part of it is very computational, right, in design, right, because, you know, you have your algorithm designs, right, so you have your model, 3D model, you can generate an optimal shape, for the internal structure based on your requirements with just a little bit of code, right? So it's kind of amazing like where that direction is heading. But also, it's very much still a hardware based field. You can't have avionics without an airplane, you know, just to be quite frank, right? Like you can't just code your way out of everything. And it's a very interesting thing because there's a group of people out there that are super passionate about code and computers and electronics that they don't realize that the core of an airplane, the heart of an airplane, is the structure, right? They think it's like, oh, it's easy to create structure, which relatively speaking maybe, but I feel like the future is both still. It's not just AI, generative design, smart avionics and integrated warfare and whatnot. That may all be like the next level of capability, but at the heart, airplanes are still airplanes, right? You still need a physical body for the to carry the payload or the pilot. Maybe even it's going to be pilotless in the future, but you're not going to fly anywhere without a payload, right? Because even if your mission is completely electronic, you still need a sensor suite to take information, to get that data, right? To know where a certain enemy is or whatnot. And there's still a lot of room to grow in hardware. And a lot of that is in design and also material science, right? Design and material science kind of go hand in hand in the field because new materials enable new capabilities, right? And with new capabilities, you can have new optimizations and new designs that work with that specific material. So, things like 3D printing we're seeing nowadays, where you're printing, you're sintering metal powder into aerospace grade parts, and that's like the next leap, right? And what can you do, right, with that new material science? You can create highly optimized and intricate shapes that you wouldn't be able to create with subtractive manufacturing, which is just kind of the standard of what we do right now. Is everything is machined, right? If you look inside, for example, I work on jet engines. If you look at a blisk, a rotor blisk, right? It's a one piece of titanium that's like a circle, and then you machine out everything to the point where you have blades, right, integrated. It's called an IBR, like that's the proper term. It's an IBR, integrated blisk or bladed rotor, something like that. But I don't actually work on the blisk, I work on some other parts, but you get the idea. Is that most of the manufacturing right now is still very much subtractive, right? It's not 3D printed, but once you unlock that new material science and new technology there, it's very easy to, or it's not very easy, I'm just making up stuff. It's beneficial, it's highly beneficial to redesign these parts, reimagine these parts for that new technology, right? You can get performance leaps. If you look on YouTube of things like generative CAD design, right? It's amazing what we're able to do, right? I saw this guy, he in this video, he literally had this bookshelf stand, right? It was like a triangular piece that holds up books, right? You nail it or screw it into the wall, and he essentially had a whole triangle full of material, and you're able to computationally apply a load on that workpiece, on that part, and subtract out the material that has the lowest lowest stress, specific stress, right? So they normalize the stress by the volume of material that is needed to support that stress. And it's amazing. Like the shapes that you get out of generative design look so organic and alien-like. It's like a next leap in design, really, because it's highly efficient, right? It's like the most optimized, the correct, proper solution for that given set of boundary conditions, which is quite amazing. That's like kind of the future for design, but for now, it is still very much subtractive manufacturing, which is also what we're doing here. We're just cutting some paper, but the spirit and the idea is there, right? And so implementing that, taking that next step will really, really take aerospace a great leap forward. So it's still exciting. A lot of opportunities in hardware, in aero structures, so to speak, for innovation and advancement. It's not easy, right? If it were easy, we would think, it's already conquered, but there's always, performance enhancements with new material science and just really going deep into the physics of, the mechanics of materials. It's amazing how deep you can go, and still have more to learn. So we have the wings and the tails done. For now, we only need one set, right? Tail and wing to really model the aircraft. So right now we're trying to make an F-16. If you just joined the stream, we're trying to make an F-16. The general plan is to integrate a new mechanism that I designed for the Astra right here, which is the leading edge slat. Well, it's covered up now, so you can't really see. But this mechanism down here that controls the slats, I want to implement that, and also at the same time take it a step further, right? I want to implement that mechanism, but also now that we have a tail in the back instead of canard in the front, we can link the mechanism together since both surfaces turn in the same direction. So that's kind of the goal right now. I don't know how it's gonna turn out. This is still very much an experiment because I've never done it before. But, with these live streams, I'm just capturing everything. I'm not gonna edit this out. If it succeeds, then it succeeds. If it doesn't, then, oh well, right? So, right now, I think I want to cut out the, so make a fold real quick, and then mark out where the slats come out, and then cut that. I might do that for the other wing too. I will actually do that for the other wing as well. So I'm gonna need my iPad for that, just because that's where I got the drawing. That's where I have it. So I'm just gonna lock this in place so it doesn't move. All right, so we have our wing here, which goes out like this, right? The thinner part is on the outside, right? And really, honestly, I think the best way to do this is, we should have done it really on this design, but it's kind of weird. I'm just trying to think right now. This is interesting because I think essentially what we're gonna have to do, I don't know if I want the slats to be the same color. Should I have it be the same color? Should I change it to white or orange or something? Because on the Astra, it is orange, right? So let me know if you have like a specific request, but I think I'm gonna go with this gray or possibly a white. The gray would be kind of hard because we would have to cut out a piece that would match this plan form, but since the wing and the slats have thickness, it's going to take away from some of that. So it's going to be actually a little bit off. We need to modify the shape a little to get it to be properly seated. Just going to take a sip real quick. All right. Yeah, this is interesting. I think I'm gonna cut a template, trace a template based off of the slats, and work with that. Looks like this is actually the hinge line, so I'm gonna go right in between. Try and capture this shape right here. Alright, so that's the template. Yeah, we don't actually need to draw lines for this. We can just, because it's such a short edge, you can just directly cut that and cut this and then fold it. Alright, we have the piece right here. We have I'll turn it around. Just make it a little easier. Lift this piece up, and then align this edge with the 2 points. Just fold that. So this is going to be a dual purpose template, because I'm thinking right now what we want to do with this template is mark out the areas to cut out from the wing itself. But also make a part that I don't know, make the part itself, make the slat. I don't know if I should use a separate piece or the same piece, make another slat, because the tolerances are a little off if I just use the piece that's cut out. Now the plus side is save some material. It's one benefit. Also saves time. And I'm not sure if the gap is going to be substantial enough to warrant a whole new piece. I'm still trying to decide here, because essentially this is what it's going to look like. Seems a little bit off. I'm not sure why. I should make a preliminary fold. Just gonna mark out the vertices here. Try and get a line. Okay, let's move this line. good. Maybe that edge isn't straight. That's why it looks off. Yeah, it's a little bit slanted for some reason. Okay, we can work with that. This is the right shape for the slat, I believe. And then it ends right here. So instead of, well, it's gonna be separated into two pieces anyway, right? Or three pieces in this case: the top, the bottom, and the slat itself. That looks kind of right. I'm not sure. I just need to check against the template. Looks like it tapers a little bit more. Oh, I took the midpoint of the hinge line. Just lock it. So essentially what I did was I didn't take this shape. I took a little bit more. You see those two dotted lines? Yeah, that's like kind of, that's where I drew the line here instead of the edge there. I think I did that because I didn't want the tip to be too thin. That would have been kind of bad. Just because, you know, the tolerance is just not going to work out. But you know, it looks all right. Doesn't look too bad. This is going to be an interesting project. So I think this is decent. Maybe it'll look better with an actual fuselage right here. Right, because if we line it up, see what it looks like in proportion to the rest of it. Okay, it looks a little off, but I also don't want it to be too thin. I want to modify it a little bit. So right now we're at point. You'll notice I mixed units, and that's just the way I do things. It doesn't matter. This is not critical. Just change the shape a little bit, but this I think looks a little better. I don't know how the slats might integrate into this, but because that's a very tiny surface right there, but we'll see how it goes. Okay, so this is gonna be interesting. I need to cut this apart. And also, yeah, I'm gonna need a straight edge cutter for that. But then, if I cut this first, I can flip it over and then trace out the shape, and then cut it again. So I think I will just do that. Just move my stuff out of the way. Okay, so the plan right now is to carefully, very carefully, cut along this edge. To that location. Whew, all right, that's a very, very clean, very close cut. And then you just like trim a little bit there. Okay, and then this is gonna come right here. Okay. You might be saying, "Oh my goodness, you just cut the template that you made." And I would agree with you. That's kind of kind of, if this is not correct, then we have to do it all over again. But I have a feeling this is going to be right. So put this underneath, put a straight edge right on this line. We are going to fold this. Pinch it and fold it. Have it come over to the other side. Nice video, greetings. Thanks, FPV Stealth RC. Okay. Just tracing the shape here. Okay, just made that cut. This is gonna be a little bit trickier because this is not a flat part anymore. I want to cut a straight edge into it. So let's see how that goes. This is aligned. All right. Oh, okay. Just a tiny bit over, but that shouldn't be a deal breaker. All right. So we have our part here. This is the leading edge slat. I'm gonna keep this, and the wing right here goes right here, and this part just fits right out here. So I will show you how to assemble this. This is kind of the core advancement innovation in the M1, in the YX10 M1. How did I get this? Right, this is the core technology of this design, is the integration of all the structure inside, right? You don't see it because it's all hidden inside, but it's I think it's a very clever way to do things, but we'll see. It's really simple when you get down to it. The solution is often simpler than the answers that you come up with. I spent a ton of time designing that mechanism, but in the end, it just took a little bit of imagining, and you're gonna say, oh my goodness, like that was the solution this whole time? Like, come on. Like, it's not some groundbreaking design. It's just literally a very thin bearing, which is very important. I will show how to make that. But in the meantime, let's look at this and see how to apply this. Not sure if I want to do that or the other way. If I want both to be on top, one to be on bottom. I feel like I should have both on top because the spar design for this aircraft is going to be interesting. It's not going to be very straightforward. I'm thinking of incorporating 2 spars. That's not for sake of, structural rigidity or anything. It's literally because the mechanism requires a spar to actuate along. So This looks decent. Okay. You know what? I think I'm gonna tape this down. This top layer we will re-examine later. But also before I do that, before I tape that in place, I just want to get this wing all set to go exactly like that. So this, I'm gonna label this real quick, just so, right, just so we have a reference. This is the right side wing. Just labeling it, keeping track. This is the right slat. Okay. I want to do the same thing here. We already have the template. It's just a matter of getting it made. Okay, let's mark the vertex here, vertex here. And just draw a straight line between both. Right. Looks pretty clean. And we'll do the same thing that we did to this, as you know, we have the markings, so it's all set to go. We just need to do it, but right now we want to focus on doing this part right here. All right, so we've got a slot right there. Right, we want to tape the base of the wing down. Right. So this is going to be interesting. Get the length of the root here. That's the base, because this one is the top cover. Alright, so right here, I'm going to tape the half of the tape on the part. Standard procedure for taping. Just lift this up a little bit. Remove that wrinkle. Okay. And align the leading edge right to that line. Pretty close, right? It's always going to be a little bit off, but it's within my tolerance standards. Okay, so we should tape these little bits here, and we should be all set to go to start work on the mechanism. Whoa. Pretty good. I'm just gonna trim off this little tiny bit here. Right. Okay, looks pretty pretty good. Then the rear portion here. Fighting Falcon. I think the nickname for this plane is actually Viper, which is interesting. It's not the official name, right? The official name is Fighting Falcon, but it's interesting how the nickname of this plane is Viper. Yeah, that looks pretty good. All right, so I'm wondering if I should cut the other wing and get it assembled. Because when we work on the mechanism, we don't want to finish one mechanism completely. We want to try and copy the parts that were made for the other side. So, interesting food for thought. I think I will actually do that. I'm gonna cut the other side and tape it down. This is progress. We're making progress. It's taking a lot of time right now, but the quality will speak for itself down the line. That is the plan, right? Good things take time. That's just how it is. So we're gonna make this cut right here. And make that cut with the cutting board. Clean cut, very nice. And then just kind of finish this off. All right. And okay, so we have one of the other side done. Just gonna need our other ruler here. I love this ruler. This is a nice ruler from Muji. If you've ever gone into one of their stores, they make these really nice stationery items. This is like a very minimal, very clean aluminum ruler. I'm thinking of getting another one of these, maybe a larger version of this, because this plastic one is a little rough. I think I want to replace that, but I also need inches, which Muji rulers don't tend to have. Literally nobody else in the world uses imperial. Only U.S. and maybe England. I don't even think England uses it anymore. It's like KG and whatnot over there. But anyways, U.S. is gonna be U.S. for a long time. Again, our mixed units. It's not the best thing in the world, but alright, I'm just trying to get it so that the shadow isn't interfering with my judgment of where it is. Cool. That's it. Yep. Okay. Fold it over. Okay, looks pretty good. just need to cut the rest of this out. Use scissors for the small cut. And then for the long cut, I'm going to use our cutter here. I'm going to fold this a little bit flatter to get it to fit. Okay. Looks pretty good to me. Slice and nice. Slice and nice. Wow, what a poet. Anyway, we have the other wing ready to go. Now it's the question of which is which. Does it really matter? If they're matching, then it doesn't really matter too much. I'm gonna have, oh shoot, it's gonna go the other way, right? It's gonna go like this or like this. Which way do I want it to go? I think I want it to go like this. This one is slightly bigger, just from the tolerances of cutting and whatnot. This will be perfect. There's a little gap there, but it should be okay. Really just aligning this part. This is going to take a little bit of time to get right. I'm matching the trailing edges because that's a very noticeable thing. It looks like the front. Oh shoot, my hand. Hand-eye coordination. Right. Sure that's good. That's all set. And then this is all set as well. All right. Okay. Really secure that down. Really tight and nice and lean and clean. Okay, just get that length there. And tape that down. Great. That looks solid. On the back here. Just need to get length of tape. Okay. Great. Okay, we have our wing base ready to go. I'm just gonna label this one left. Okay. And shoot, which one? This is the top cover for the right. And this is the top cover for the left. I'm just gonna label that real quick. Left. And the slat itself is also on the left side. So gotta label that with L. Okay. And we're all set to go. So I'm gonna put the left parts to the side for now and work on the right. So this is going to be interesting. Okay. This is kind of where things start to get a little bit more complicated, because you need some mechanism to work off of to really get started here. Some like structure, right? So I think what we're gonna do is we're gonna get the center line main actuation rod ready to go. It's gonna be kind of hard, but let's see if I can. Okay, I'm running low on these. I need to get more of these. Shoot, this one's kind of broken. Let's see if there's another one. Okay, I can use this for something else. Go from the very tippy tip to the back. I want to just mark out real quick where some major features are. I'm gonna rotate it because we're gonna need these lines on the side. Before I do that, let me get the center line marked out. This is 5.4 centimeters. Half of that is going to be 2.7. All right, looks good. This right here is 4 centimeters. Wow, that's really nice. I'm just gonna mark at 2. Okay, and then we're just gonna mark a center line. This aircraft. Alright, we have a center line, and I'm just going to draw an extension of this root right here. This is the trailing edge of the slat, but it's where the wing actually starts, I guess, you know. This is for reference, because we need to make the mechanism align with this. Yeah, the actuation portion is a hinge that is cleverly integrated into the spar, but you will see that potentially today, maybe next stream, but we'll see how far we get. So the tail would be interesting to look at right now, because this is really laying out the groundwork for all of the mechanism details. So this is interesting. I don't know where exactly it starts to pivot. I need to research that, because it doesn't pivot, you know, like that, obviously. It's somewhere in the middle, but where, right? That's the question. All moving control surface. That's going to be very interesting. I'm gonna just take 1/2 of this chord. This is 4.6, 4.7, so like 2.3, a little over that. 2.35 would be okay. This is kind of where the actuation rod needs to come in, and I just like match this shape. It needs to be linked to the other side as well. So this is kind of where mechanisms are hard to make. It's if you want to make it precise, that is, right? If you want to make it crude, it's really quick. But if you want to make it properly and make it really precise and machine-like, it's going to take some time, especially because we don't have the proper tools, right? We were just bending some wire into place. But this is good. And with this location marked out right at 1/2 here, if we align the leading edge and this 1/2, this 1/2 actually lines up perfectly with where the engine nozzle starts, or whatever feature that I cut out here. So I'm gonna mark that right here, and we are going to extend that mark to the other side here. This is the hinge line. This is the elevator. Leading edge. This is the hinge line. Or I guess it's more of a fulcrum, I guess, but rotation point, right? But I'll just call it hinge. On the other side, this is right. We really only need one side labeled for this. This, I don't think I need to mark. This is like the leading edge, but there's not enough space here to write that. This is, I guess, yeah, I'll just leave that as it is. This is just for reference later on. Okay, so yeah, this is going to be interesting. This is a very tight space to integrate a mechanism. Yeah, I'm not sure how I want to go about this. I think we might need to extend it with a nozzle-like structure, just to get it to, because what we typically do for this type of mechanism is we use these brass fasteners, and you need a little bit of surface to really, hold the hinge in place. And right now this doesn't really have all that much. I'm thinking like you could puncture one side and really just push it all the way through and then fold both forward, but that's just, it's not very elegant. you could do it this way, I guess. I mean, I guess I could just do it like this. This is a new method, and then bend the head perpendicular to this, right? So like bend this 90 degrees that way. But we'll cross that bridge when we get there. Right now this looks good. We just need to have the things in place. So the mechanism, I'm thinking we really need to understand how it's gonna move, right? So let's clean this off. All right, so this is the mechanism right here. All right, so that's gonna be the engine nozzle and whatnot, and if we align this with the, we call this the, so now that we have a center line, we can now mark, or align this and then mark out. This is the elevator leading edge. Wing trailing edge. This is kind of where it meets. This one is critical. This is where the mechanism ends. So if you go one way, I think I just got a comment. Let me just look at the comment real quick. This is, oh god, this this thing is leaking all over the place. Dang. All right. Let's see if I have a napkin or something. Bye. Damn, I hate it when like things just go wrong. You got like pens leaking and whatnot. Alright. Not too bad, I guess. Let's put this to the side. Okay. Yeah, I was gonna read that comment. I think I got a comment earlier from Benjamin Rogers. Could you connect the exhaust nozzle to the mechanism so it could pivot with the stabilizers? I don't know if the F-16 ever had thrust vectoring unless you count the Vista model, which was used as a test bed. The F-16 did not incorporate thrust vectoring. The Vista, I think it might have, but that was more, if I recall correctly, it's more of a electronic test bed, but I might be completely wrong. I don't recall any F-16 model having thrust vectoring. You might be thinking of the F-15, which does. You know, there was one F-15 variant, the active, the, you know, SMTD, the Stovall version of that with the canards, and it kind of looks weird. I kind of want to build that, actually. That might be a next build after an F-15 or something. But yeah, the F-15 active does have thrust vectoring. It has, like, you know, 2D pitch, and I think it might have had yaw thrust vectoring capability, but I'm not sure. That is an interesting idea, making the nozzle rotate, but I feel like that, you know, I would rather have just the standard push-pull method. But that's something to keep in mind. That's a very good idea, Benjamin Rogers. I appreciate that. I will keep that in mind, potentially for, you know, something like a Sukhoi Su-30 or something, because that's an elegant way to implement a mechanism, right? Instead of having a knob that sticks out like a sore thumb, you have it integrated into the nozzles, and when you turn the nozzles, you can turn the surfaces all at once, which is very interesting. But now that I actually think about it, I'm not sure if that's entirely possible. You would have to link the mechanism in a way that doesn't involve so much friction, because if you bend it and there's a ton of friction and it doesn't want to budge, then you're applying a lot of stress at one end. The whole idea with the sliding mechanism is that with one action, you can kind of piggyback off of that motion, right? That linear motion, and then convert it into rotational motion with a mechanism. But when your input is a rotational input, you might have some stress concentrations or whatnot, just like because it's such a tight area back here, or just in the mechanism, right? If you turn and you have such a small moment arm to push this inner rod forward, you might actually end up breaking the rod. But I don't know. I'm just thinking about how exactly we're going to implement that. But that is a great idea. I might look into that. I think a potential way around that would be like some type of 4-bar linkage, which is going to be a little bit more complicated. But I think it might be possible with a 3-bar linkage, because the fuselage itself acts as a linkage, right? So you imagine like you have your ground. Imagine this line is the ground, right? You can have 2 bars here and 1 bar in between connecting them, and they could rotate at the same time, right? That's kind of a 4-bar linkage. The 4th bar just happens to be the fuselage. So I was thinking maybe a mechanism like that, could link, 3 different things, right? You have your leading edge slats, you have your elevator, you have your nozzle, and you could turn all of them at once, synchronized. But the metal work behind that, just to get the hinges working, and it's going to be a lot of metal bending and a lot of struggle there. So it's definitely possible. It's just, do you want to take the effort and manufacture something like that? I guess, with the methodologies that you have for manufacturing, is it going to be of decent quality? That's kind of the trade-off here. You kind of have to think about that, because there are infinite possibilities really for mechanisms, but you want one that is reliable and easy enough to make, right? But yeah, that's definitely possible. But also another issue with that, linkage, the 3 or 6-bar linkage or 4-bar linkage, is that you don't really get to control how, like, where it stops, right? This is like a free pivot. You would have to apply a ton of friction at the root, right, at the fulcrum area, to get it to stay at a certain position. Whereas with a linear actuation mechanism, you have a ton of friction all along this tube that keeps the mechanism stable and in place. So that's kind of why I usually go with a linear mechanism rather than, like, say, a turning mechanism. But the only thing I can think about, like, for turning would be like a screw, right? So if you have like a engine nozzle that you can actually turn, and it activates a screw gear, and then you have a bunch of mechanisms bleeding off of that central screw, that would be highly effective, right? Because the screw gear, you can't reverse actuate it through the output, right? Your input determines the output, but then your output is really, it cannot determine the input knob, right? So you have like a nozzle here that can be turned, like, not up and down in pitch, but in rotation. You can create some really neat designs. But the problem with that is you need like a worm gear drive that you can bleed off mechanical motion into, and manufacturing a gear is outside of my current capabilities. But maybe in the future with 3D printing, like, I can make a mechanism with a turnable nozzle, with, you know, a very nicely made mechanism for actuating the slats and the elevators. You just turn the nozzle, and you don't have that unsightly linear actuator knob at the back. So that might be another idea that you can try and implement, but that's maybe for another time. Because right now with what I have, I can only really create these mechanisms through office supplies. But yeah, I might, you know, I got a 3D printer for my dad, so I might be able to print some parts, but I still need to like be able to model like a screw, and you have to be able to print it, right? And it's like hard to print things that don't have support edges. It's just a whole can of worms in and of itself. So every method is gonna have its own difficulties. So whatever you pursue, you know, it's gonna be deep if you want to get it to work well. All right, so we have the major features marked out. We have the wings taped on. This is going to be interesting. I think the next step is to mark on, well, I mean, we already did on the main actuation rod here, the parts where we want to cut out. So I have a new methodology for implementing mechanisms, because as you notice here, the YX10 is actually a hybrid of different mechanisms, right? So I started off making the same mechanism that I made for the first version of the Astra, which is this kind of actuation mechanism that pulls. I mean, it's still gonna pull, right? It's just this entire front piece here moves, which kind of bothers me because that's a lot of stuff out in the open, so to speak, and it's just like moving. But what I did on the underside for the leading edge slats was I actually cut little slots in the straw. You can't see it here, unfortunately, because I covered it up, but the straw itself has some, you know, holes in it, and I was able to, it's kind of like a slotted mechanism, right? If you think about like a rifle or a gun, right, you have like a tube with a cutout and a pin going through it. That's kind of what I did for the bottom here. And it's, you know, I was testing out new methodologies, right? This is untested before. What I did here was kind of risky in the sense that if you have like a you know, piece of straw and you puncture it with a metal rod, which is not very flexible compared to the straw, right? Because the straw is plastic and the metal itself is, well, it's metal, it's a lot tougher. So when you actuate the mechanism, you want to be able to make sure that this metal rod isn't going to rip through the straw, which I thought was going to be a problem. So my, you know, solution for that was to wrap a bunch of tape around and put it through, because that reinforced the plastic around the, you know, the core of the fulcrum, right, where you puncture the straw with a metal rod. But it's kind of like a balancing act, right? You know that this mechanism isn't gonna take a ton of load, right? It's only gonna take aero loads, and you know, because it's protected by the nose to wingtip geometry, so it's not really gonna be exposed to too much load. So this mechanism is actually gonna work for that. I'm not sure if, well, I mean, for the leading edge slats, this is the mechanism that I went with, right? Which works, but I'm saying like the same concept of that hole inside the rod itself, you know, slot, that might be better for cleaning up this design right here. So with the new design for this F16, I can have a solid straw all the way up until the nose, and that'll act as a better structural support too. And instead of having this whole chunk that moves forward and back, I can cut a slot, which makes it easier in certain ways to make this mechanism. So yeah, that's kind of my new idea here. It might be kind of hard to visualize until it's actually here, but the thinking behind it is there, and it's fairly ready to go. It's just a matter of actually doing it. That's why I kind of marked out, you know, where the thing meets the thing, where the where the trailing edge of the slats meet the center actuation mechanism. This is kind of where it ends, right? Your slats deploy from, you know, flat to down. It doesn't go up. So this is the back of a mechanism, if that makes any sense, right? So if we rotate it, the slot ends right here, right? Because the mechanism itself is, I don't have a sketch of it. I should make a drawing of it to better illustrate my ideas, but it really ends where you want it to be flat, if that makes any sense. But you'll definitely see as I build, you know, you'll see how things fit together. It's just a very very complicated mechanism. But it's beautiful, and that's really all I want to do, you know, is create beautiful things. So let's see, this carries over here, and you'll notice I used these lines from the straw itself to mark the location for the slots. You don't want to make it too large or too small, right? You want to make it just enough. So how much do I want the thing to turn? If I want 45 degrees of slat motion, right? 45 degrees into the page like that, then I need to account for the fact that if I have a vertical rod here, it's gonna turn 45 degrees. So really all we need is this much, but we need to give ourselves some margin. So maybe about here. Let's see how aligned this is. I'm thinking 1 centimeter should be enough of a slat, or of a slot for this, right? Even if you rotate fully down to 90 degrees, it's gonna be about 1 centimeter. So 1 centimeter seems like a good place to cap the length of the slot. So it's kind of where I want it to end. Just need to carry that mark over here. Then also on the other side. This is mechanism design is, to me, it's very exciting. It's a combination of mechanical, you know, engineering and materials and stress and whatnot, but you also have kinematics, which is how things move, which, you know, there are computer programs out there for envisioning that, and that's definitely useful for more complicated mechanisms. But for things like this, it's really nice to see something work after you think about it and implement it, you know. I just think that's so cool. So mechanisms, there's like an allure to them, you know, like when you see GIFs of mechanisms actuating, it's just, to me, it's just exciting. It's like watching gears turn, right, and watching levers being pulled. It's just exciting. And airplanes are full of mechanisms, and they're truly machines, right? Not only in like the airframe, but also in the jet engines and landing gear, for example, right? It's all mechanical. So it's exciting. It gives the aircraft life, right? And that life is what I'm trying to capture by implementing these mechanisms. You can definitely create a paper airplane without any of these, But it's just, to me, doing that is kind of boring, right? You have to try and push yourself and really try and understand physics and, you know, trying to do something cool, something new, right? And I don't think anybody has ever put mechanisms in something as trivial as a paper airplane. So it's a good testing ground for ideas and experimentation, right? Because as I said, right now I'm living in an apartment. I don't have like access to, you know, I don't have the infrastructure in place to work on RC planes. But the idea is once I, you know, learn and apply these rules and design methodologies here, I can apply it later on to all sorts of different projects, including RC planes. And that's going to be an interesting new shift, right, for this channel. But that's still a couple years away. I'm, you know, saving up for like a place, like a more permanent condo or house or something. But it's just, it'll take some time to get there, and I'm working with what I have right now to really push the limits of these things. So anyways, we're kind of running long here. Usually I ended at about 2 hours, about 130 minutes, 20 to 30 minutes. So I don't know how long I'm going to continue this, but I think it's like 8 minutes or so, 8 to 18 minutes. So I'm just going to mark out for the rest of today. You know, it doesn't look like we did a lot, but you know, the thinking behind all of this is, you know, useful, right? At least I would like to think that it is useful. But it's a lot of design is just thinking about the problem. It's not actually doing. But you know, you want to have a good balance of both, right? You can't think forever. And that's kind of the issue that I have a lot of the time is that I think forever. So with these streams, I'm hoping to kick myself back into the mode of, you know, like actually doing something. These 2 points I don't really need. I just probably like fade that out a little bit, but this is like Sharpie marker, so it's kind of permanent. I'm trying to mark out the location where I should probably cap this, but I'm not gonna draw it real quick. The location of the, you know, the slot for this, because we want it to be able to pitch down and also up, right? So how much do we need is the question here. This is, so in case you're new to the stream, I think there's somebody new who joined, but we're making an F-16, trying to incorporate some new mechanisms that we developed, or that I developed with the Astra right here. We're just trying to incorporate this slat mechanism and copy this for the tail here. So this is kind of the behind the scenes of how I make these things. So yeah, this is gonna be interesting. So I don't know if, so it has to come over, right? So this linkage has to come over and connect, right? And then go out to the control surfaces here, right? So like that, and so that's the hinge line. Then how long do we want that moment arm? So it doesn't actually have to come here. Now that I think about it, if the slot is here and your rod comes all the way here, right, then you can really, you can pull, right, if it's, let's say, let's pick a good number here. Let's say it's 2 centimeters, right, the actuation arm. If it's 2 centimeters, then from 2 centimeters at this location, you can pull or push, which will activate that mechanism. Maybe we don't need we don't need 2, we need like 1.5. That looks more appropriate. Turning the tube to the side so we can get a better feel for where it's going to be. I'm using pencil right now. Pencil, this is 0.5 HB. Makes a very light mark on plastic. You probably can't see it from here, but I assure you there is a mark. This is less permanent than Sharpie, so that's why I'm working with that. Okay, so 1.5. Right, so this is kind of where neutral position of the elevator is going to be. Right, so you have your vertical bar connecting the two control surfaces, and then you have this link that's going to come up diagonally to wind around that to turn it. So if this is neutral, I apologize for that. Some people are driving really loudly. If this is neutral position, if we want to pitch down, we move forward, we push forward, and if we want to move back, we can pull back. So it's just a matter of envisioning, like, okay, this location, if I push back 1 centimeter, 1 centimeter is a lot of actuation space, actually, when I think about it. So maybe we should just go with 1, right? Leave some extra wiggle room for potential movement. So let's give it 1 on each side. Although I doubt I will be using pitch down actuation. It's still nice to have that option, right? Or actually, when I think about it, when I push forward, it's actually going to pitch this down, which is going to pitch the plane up. So actually pushing forward means pulling up in this case. So this is nice. So this is neutral position. I can let's see. It depends on how tall this leg is connecting these two surfaces, right? So if it's taller, then I need more space to move, but I think it's gonna be enough. I think 1 centimeter should be enough here. So we're just gonna keep it at that. Yeah, so this is kind of where we want the mechanism slot to be. This is neutral, and we're gonna mark that out. This is kind of hard to see, I'm so sorry. You guys can't really see this clearly, it's kind of blurry, but I'm gonna mark out neutral position here. This is N. Right, I'm just gonna mark it down the center line properly here, and then copy this. And then copy this one. All right, and then I'm going to label this pitch up, down, neutral. God, this is gonna be kind of hard. We need some new symbols. Let's see. This is the front here, right? So this, I'm gonna mark actuation mechanisms with a plus. Right? That kind of defines the limit here. plus back here. And then this is, yeah, I really shouldn't have made those two marks. That's gonna be kind of hard. This is, so these plus marks I'm gonna define as control points for the mechanism. Right. I'm just gonna write off to the side here. This is gonna be neutral. This is going to be pitched down. So I'm gonna give it a letter D and then pitch up. There. Okay. I'm just labeling things for sake of clarity. This is also going to be kind of similar here. Right. This is going to be neutral or undeployed and then deployed. So this is neutral position. Neutral. And down. Right. So that's kind of a prototype, right? Marking behind that. All right, so we're gonna run a little long here, but next step would be to cut out the slots and then puncture the center rod. We need to make a center rod. This is still empty right now, but we need to make like a twin straw friction fit, friction lock mechanism. And once we do that, we can puncture it at the neutral position and then start to shape the mechanism around that and link it up. So this is going to take some time. I realize, this is not a very straightforward process, but hopefully the end product will be quite unique and interesting instead of just, a regular paper airplane. So for now, I don't know if I want to actually do that yet. I kind of want to end the stream here. Is a good stopping place, but we will definitely continue this journey of making an F-16 with leading edge slats and elevators linked by one core mechanism. This is really cool. I've actually never done this. In the YX-10, it's the mechanisms are separated by a piece of cardstock or cardboard, right? There's two separate mechanisms, so it makes it relatively heavy, which I'm kind of worried about. It might not fly too well now that there's two mechanisms, but the idea behind this is to, I guess, develop a M2 prototype. You can have a mechanism that links both the slats and the trailing edge together. That's kind of amazing. It reduces so much complexity, right? The M1 really kind of pointed me in that direction, so it's not all for nothing, right? This mechanism is the heart and is like kind of the base where we built off of. But now with this new slot configuration for the mechanism is, you have a slot for a pin that moves back and forth because you actuate the the center column back and forth, and so it's just a very clean way to integrate this mechanism, and we're able to link the two mechanisms together in the F-16 because of its configuration. So it might not actually be possible. I haven't thought of a way to do it for a canard configuration where you have planes in the front, because then your slats and your canards are going in opposite directions, and then you can't really synchronize that with a mechanism on one plane, right? You need to cross over the line of actuation to get the opposite movement. And so that's really a problem for canard designs, but maybe I'll figure out something else in the future for that. But for the F-16, it's definitely a configuration where I can make the mechanism possible, like just link it together. And what we did today, you know, we worked off of the fuselage. We got the templates done for the tail and wing surfaces, right? We cut out the actual parts. They're ready to go. It's just a matter of, you know, integrating it with the mechanism, right? So, you know, we also started off with a center column, like this friction fit architecture, right? And then we made some marks on, you know, we kind of just eyeballed it, but we really found out where the actuation line was going to be, right? We drew that line. We determined this position to be neutral. We said if we push forward the rod, we want it to deploy the slats. So this is deployed, D for deployed, N for neutral, right? And then for the aft, we're also, you know, doing the same thing here with neutral, right? A diagonal piece is going to connect to this hinge line, right? Neutral. Forward is up, right? It's going to pitch down, but it's going to pitch the plane up. So that's why I put it as U, and then D is going to be down. When you pull back, it's going to rotate this arm back, which is going to pull the surface like this, which is going to pitch the plane down. So, so I guess by that convention, this should actually be a U, but anyways, I know what it does, so that's all I need to really know. The really important bit is that you mark the neutral positions in this mechanism, right? It's just, that's where you want to build your default configuration off of. And then once you have that, you can shift it back and forth and it'll move. But that's a story for the next stream. We marked out these locations this time, but next time we can actually cut out the slots and start building the center column here, puncture it, and then build the mechanisms out to the wings and the tail. So that's kind of the plan for next time. Sorry, I just like explained my entire process without showing anything, but these things, they take some time, right? It's gonna take some time to get this right, but I think it's gonna be really interesting and cool once I get it to work. So yeah, that's pretty much it for this stream. I have 2 minutes. If anyone has any questions or anything, feel free to leave a comment or a chat, but I think I might be ending the stream soon, so you know, just leave a comment once it's published or DM me. Feel free to connect with me on my Instagram. It's at ben.fellow, but you know, there's also a Y13A design account that you can reach out to. But if you have any questions, feel free to ask. And I guess that's pretty much it for this time. Really just trying to get the heart and soul of this aircraft, which is the mechanism, ready to go. And then after this is built, then comes the fun part of, you know, modeling the fuselage, making it look all nice, right, with the tail and whatnot. But that's the story for maybe a couple streams down the road. We really want to just get the mechanism working, which I think is the coolest part about this project. We don't have any moving parts yet, but we're getting there, right? So, all right, guys, thanks for watching. Keep safe. You know, it's a crazy world out there. Have a happy 4th of July, and you know, I will probably stream again next week on Friday, but you know, I have like Friday off, so I don't know, I might do another stream earlier than that, but I will see you guys in the next stream. And take care, work on your own projects, and yeah, that's pretty much it. So cool, thanks, talk to you guys later.